All right. Thanks, Ray. And also thanks to the other organizers for inviting me to come and give this lecture series. I would say that I'm a relative beginner in non-commutative geometry, non-commutative differential geometry compared to many people in this room. So when I was asked if I wanted to give this lecture series, I have to imagine that you would like some maybe different perspective on things. Some reasons why I find this a good approach to non-commutative differential geometry. So I'm going to try to provide maybe a slightly different perspective to things. And therefore, the lectures are going to be organized in the following way. So for lecture 1, I'm going to talk about what is a differential calculus. Hopefully, if I have time, what's an exterior algebra? For lecture 2, I want to talk about, from my perspective, why. Why would you expect differential calculi to provide a good generalization of classical differential geometry to the non-commutative setting? And my reasons for seeing it in this way basically goes through some foundational stuff in differential geometry. We're not going to talk about like charts and atlases and that stuff. I'm going to assume that manifolds have been defined. But we are going to talk a bit about the structure of natural operations and categorical constructions in differential geometry. What exactly naturality means and why it's more or less possible to capture it through a differential calculus. And after lecture 2, we know what we're talking about. We know why we should care. Then we want to talk about where. Because once you have defined differential calculi and you see that you can make nice geometry with them, the problem is that typically, well, just a tangent, typically when I give a talk about these things, the first questions I get is something like, so what are the differential operators on 2x2 matrices? And then I have to admit, I don't know because I don't have a calculi. It's not really functorial in the algebra itself. The calculus is extra data. But if you have an algebra that is equipped with some other kind of additional data, then you can construct a calculus from that data, and then it will be more or less canonically defined. And I think I will talk about 2 cases. One will be about covariant calculi, and the other will be about something relating to differential operators. So that's the plan and introduction. Let's begin with the lecture. So first, we're going to talk about algebras over commutative rings. And I don't know if most people here are used to working with fields or even complex numbers, but really the generalization to commutative rings is not a big problem. Nothing really fails, at least at this level. So let K be a commutative ring. With unit. And then an unital associative algebra over K is a K module equipped with an algebra structure. So actually, it should be a ring, which is let's actually say that differently. Not a K module, but it's a ring, unital possibly non-commutative ring. which is equipped with a homomorphism from K into the center of the ring, such that the unit acts as the unit in the algebra. And some examples of these things I will not explain too deeply, but the rational numbers form an algebra over the integers with the map that takes x to x divided by 1, the obvious thing you want to do. The matrices over the commutative ring with the matrix multiplication and the map that takes field ring elements to the multiples of the identity matrix. Or you can talk about tensor algebras. Let's say we are dealing with a field, then, and V is a vector space. Then you have an algebra structure with the tensor product as the algebra operation. And you simply declare that the zero-order tensor product is the field itself. And this is universal in associative algebras with units. So another thing you can do is take tensor products modulo some ideal. And from this, Clifford algebras form a very nice example. For example, you can do something like the CLF. So we take the ideal generated by X, tensor X. Plus X squared. And well, this is one specific example, but algebras of this form are basically the most general finitely generated associative unital algebras. And of course, to get the unit, you just take the projection of the unit in the tensor algebra. And finally, more general things you can do. Take smooth functions on some manifold. And then you send x to the constant function with value x. And multiplication is just pointwise in the manifold. So this is not the most general things you could do, but there's some rather representative examples. And you see a little bit of everything. Finitely generated, non-commutative, over a proper commutative ring. And let me just briefly remark why I stress so much this function, this homomorphism, because there's some rather strange thing you can do if you don't ask for that property. If you try to weaken this a little bit, then you can do something like this. So 2 by 2 matrices over K, and then you take phi, mapping X, to the constant matrix with value X over 2 in every parameter. And this is actually an algebra homomorphism, except it doesn't have the property that the commutative ring goes into the center, and it doesn't have the property that the image of the identity of the ring goes to the identity of the algebra. I think nobody wants to consider things like this as algebras over the ring, so that's why we have to be specific. But one interesting thing that this shows very easily is that the category of homomorphisms between unital algebras or unital algebra homomorphisms is different from the category of homomorphisms between algebras that have units, because this would be an example of the latter but not the former. So let's talk about modules. So a module is an abelian group such that you have a map A cross M to M, which we usually annotate by juxtaposition, similar to the algebra multiplication. And it should satisfy a few things. So we should distribute. And the last one is the interesting one. It uses the product. And this thing tells us that we're dealing with the left module. There's also the notions of right modules and bimodules. And the essential difference is that if you want a right module, then you should replace this axiom with the one that flips the order here. So you multiply by B, then A, M. And bimodule is one that has two operations of these kinds which commute. Okay, so normally we use this notation, and you just multiply from the left or from the right to say if it's a left or a right module, but that's a bit much. That's not the actual important difference between them. The important difference is that when you take the image from the algebra into the endomorphisms by the multiplication, in the case of left modules, you get a homomorphism into the algebra of endomorphisms. In the case of right modules, you get an anti-homomorphism. Now, given an algebra, we can make what's called the opposite algebra, where we reverse the multiplication. You just switch out the multiplication map. And since there is an anti-homomorphism, or an anti-isomorphism, I should say, from A to A up, it's easy to see that right modules are simply left modules over A up. So those two are equivalent categories. Yeah, thank you. Okay, so some typical examples of modules. Rational vector spaces. Multiplication of matrices on column vectors. Or sections of vector bundles in the last case of functions on a manifold. Where the multiplication is just given pointwise. So one more thing I would like to say along these lines is a bimodule is a left module over the tensor product algebra A times A up. Some simple definitions of modules. A module is called free if it has a basis such that any elements can be written as a unique linear combination with coefficients in the algebra. So I'm just summing over Tatas. This should be finite sums in this case. Or well, example. Free modules are just direct sums of many copies of the algebra itself. Whereas a module A is just equal to A theta for each generator theta. And the reason that I wanted to talk about that, this was just to point out one thing, which is that given an algebra, it's a free left module over itself. It's a free right module over itself, but it's not a free bimodule over itself. Because freeness is more or less equivalent to having no non-trivial relations. And for A as a module, a bimodule over itself, you have relations of the form this, which vanish, and this is a non-trivial relation for a bimodule. So instead, if you want a free bimodule over A, you should take the tensor product with itself. Okay, now final word about modules is that we can take tensor products between left and right modules and also bimodules. If L is a left module and R is a right module, then you can write the tensor product R tensor over AL as the k-fold tensor product modulo a certain ideal. Which is just moving the scalars across the tensor product. And if L happened to be a bimodule, then the tensor product over A is a right module. If R was a bimodule, then the tensor product will be a left module. If both were bimodules, then you get another bimodule out of this just by the regular multiplication from the left or from the right. Okay, so now finally, let's talk about first order calculi. So let omega 1d be a bimodule. Over A. And let D be a k-linear map. such that we have the non-commutative version of the bimodule version of the Leibniz rule. Or in other words, it's a omega-1 valued derivation on A. These guys, of course, showed up in one line in Sean's talk earlier, but I'm going to take a little bit longer with them. And secondly, we have the so-called surjectivity condition, which means that the D generates omega as a left module. And by the Leibniz rule, this means that it's also generated as a right module. Okay, so if we have this, then we call it a first order calculus over A. Now, first example, most important example maybe. Let's take the free bimodule over A. Multiplication is a bilinear map. So this is a bimodule map from the free bimodule to A. This map is obviously surjective because you have a unit. And now in the category of bimodule, we could take kernels. Let's just call this iota. And now comes the thing that you really see and then you can't unsee it. This guy looks like a first jet exact sequence, which means that this guy should be interpreted as a space of one forms because it's the kernel of a exact sequence for jets. So I'm going to just label this sequence the universal one jet exact sequence. For now, that is just a name, but it's also an interpretation. And this is the way I'm coming at it, but not really the traditional way. Traditionally, one just starts with this object and calls it the universal calculus. So let's define that. As a bimodule is the kernel of the multiplication. And the universal derivative is given by 1 tensor A minus A tensor 1. So there's actually a sign convention that appears there. In the literature, it has appeared in two different forms, as far as I know. That's always fun. So I'm going to just declare this to be the right way to do it. And we will identify differentials that differ up to a sign. So proposition, the universal calculus is a calculus. Okay, so there's just two properties that we need to check. First, the derivation property, which is simple enough. So 1 times AB minus E tensor 1. And then you can write this as pulling out the B. And okay, so that's one line proof of the derivation property. And then is the surjectivity condition. And for this, we introduce just one more piece of terminology. This is an operator which we will call the universal one prolongation operator, which takes A into one tensor A. Why is it important? Because it provides a splitting of this exact sequence, not in the category of bimodules, but in the category of right modules. Well, it's obvious here, if you multiply on the right, you get something multiplied on the right on the other side. But if you have a splitting in the category of right modules, then you can also write this as a direct sum. So this gives you a decomposition. Which can be written explicitly as so. A times B is equal to so there. We know that the free bimodule is generated by elements of this form. And from the properties of the splitting, you can see that now the kernel is generated by elements of this form as a right module, but we just showed by the Leibniz rule that it's equivalent to be generated as a left module. So now there's an obvious notion of morphisms of calculi. You have to derivations like this, then there should be an induced bimodule map. On the module. And also this diagram should commute. And obviously you can compose such maps. So this leads to the category of calculi or first order calculi. So the other important property of the universal calculus is that it's a universal object in this category, an initial object in this category satisfies a universal property. So if you have another calculus, then there exists a surjective map. And of course, this is can also be seen in the category of bimodules. So it has a kernel. And you get this exact sequence. And as I mentioned before, there's a thing with signs here, but a differential is characterized up to its sign by the ideal or sub-bimodule ND inside omega 1u. So by the definition of a calculus, the map from the free bimodule or A tensor A to omega 1d is surjective. And what we should do is show that it remains surjective if you restrict it to the universal calculus. So let's take another operator, du tilde. Which maps A tensor B to A times the universal differential of B. And this operator provides another splitting of the universal one-jet exact sequence. But this time, it's not in the category of right modules, it's in the category of left modules. You can obviously see this from the formula. Let's name this map psi. This du tilde has the property that the kernel of du tilde is contained inside the property of kernel of psi also. And now we can use the left splitting and write AB as AB times 1 plus A dub. And since 1 is always in the kernel of the differential, this part doesn't contribute. And the splitting property of this map shows that our original map psi is in fact surjective and restricted to the universal calculus as well. So set PD to be psi restricted to the universal calculus, then this gives the morphism here, and simply take ND to be the kernel in the category of bimodules, and then you obtain the exact sequence by the kernel property. So it turns out that these sub-bimodules of the universal calculus are really important. Let's name them. ND will be called the space of first-order differential relations of the and I realized writing it down that is kind of a long name. Sorry. But it turns out that this space of first-order differential relations are really important in this theory. And let's give some examples of what they look like, because they are quite interesting. So first example will be for commutative calculi. Then there's a special module called the module of Kähler differentials, which can be universally assigned to any commutative algebra. And this can be written just, of course, like this. And the differential relations are generated by things of the form du of AB, where AB is product of any two elements, minus A du B minus B du A. And when I write angle brackets, I usually mean generated as a left or right module. Sorry, this should be NK. And this guy is the initial object for calculi over commutative algebras, which satisfy the commutativity property, so they're central calculi. It's very important in algebraic geometry, for instance. But we can go a bit further and write something more interesting. Let now in particular A be the smooth functions on a manifold. And this is, of course, the prototype example for differential calculi. We're going to talk about the one forms. So we have the exterior derivative. DRAM. Sorry for the DDs. The space of first order differential relation. Okay, I have to go to local coordinates now, I'm afraid, because it's difficult to do globally. But in local coordinates, you can write them as, first of all, they're generated by the same relations that come from the Kähler differentials, because it's a central calculus. But secondly, and more interestingly, you get something that looks like the Cartan distribution from jet spaces. There should be a sum here. The only difference is that on the jet spaces, the Cartan distribution is generated by expression of this form, or rather annihilated by expressions of this form that uses actual differentials, but on the total space of the jet bundle. Now we're doing another more formal thing, which is using the universal differentials instead, but you write down exactly the same expressions. So this first order differential relations just end up encoding the same information as in the Cartan distribution. Okay, so I will write one more proposition and then I think we finish for today. Sorry, dropping the first order adjective. So you have an initial object, which is just the universal. You have a terminal object, which you can get by setting d equal to 0. And it's just a 0 module. Of course, this satisfies all the axioms that we wrote down for first order calculi. And finally, if there exists a morphism between two objects, then it's unique, and as a bimodule map, it's surjective. So let's say we have this morphism, then by definition, this has to be satisfied by the definition of a morphism between calculi. So it commutes on exact forms with the differential. And then we use the fact that it's also a bimodule map. And this property again. And since anything in the target can be written in this form, this is a surjection. Now everything is forced. There's no choices left, so it's unique. That proves the theorem. So I think we end here today, and we'll save the exterior algebras and higher order prolongations for next time.
Hi, Henrik. Here, may I have questions? Maybe I have just what happens then here. We don't use these extra relations going from a partial derivative, and you just take for the smooth functions, the indicator.
Oh, this has actually been considered classically, and it does give you something like a bundle, but it's not like there's this notion of geometric vector bundle and non-geometric vector bundles, and this is something called a non-geometric vector bundle. So it doesn't really behave well with fibers.
Okay.
So presumably the omega-1 form an order upwise morphism.
Yeah.
Partial order. Does it make sense to take max and min operations on this order?
Whenever defined. You can find very nice subcategories that admit a terminal object or an initial object, for instance. Like if you take any fixed calculus, you can say take anything that has a morphism into this. Because of composition, it will give you a subcategory that's like above it. Or on the other hand, you can take like the Kähler differentials, take some fixed calculus and take all morphisms that emit out of it, and this gives you a nice subcategory. So in these cases, it behaves very well. And I'll talk more about these kinds of categories later.
Any other questions? That's not the case, then we'll thank Henrik again.